Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series. And I am very happy to have Terese Hansen with us today. Hello, Terese.
Hello, Frank. Thank you very much for the invitation to be here and talk about my science.
Yeah, it's a really awesome paper, and we'll get to it here in a little bit. On this July 15th of 2024 as we record this. And Terese, what's your geolocation? Where are you at?
I'm in Stockholm. I'm at Stockholm University. So enjoying the long summer nights up here, which is very nice.
What time does the sun go down, by the way, roughly? What time?
I don't know, 11, something like that. I'm not actually sure. It rises very early, so it's more in the mornings that it's very bright.
Very nice, very nice. Is summer a better time to see the aurora borealis, or is that better in the winter?
Well, I guess it's better in the winter. It's more dark nights, but I haven't seen it yet. It's been several times here in Stockholm while I've been here, but I haven't been here while it's been there. So I've missed it, which is really, really sad.
That's still on my bet bucket to see that.
Yeah, me too.
Get there and see it. Great. And Terese, what's your position there in Stockholm?
I'm hired as a researcher. I have my own grant here, so I get to do exactly what I like to do, which is to do abundance analysis of stars.
Awesome. So. All right. Very cool. Which is what you like to do for research. So let's
yeah, so I mean, my primary research is abundance analysis of metal-poor stars.
Good.
Any kind of metal-poor star you can find for me. I like the ones in the halo, the ones in the dwarf galaxies that we're going to talk about today. Ones in the streams that we're finding now are particularly interesting as well. And any kind of chemical peculiarity that you can find, I would love to look at.
Very nice. Cool. And that is going to bring us to this very awesome APJ article. It is open access. It's the open access era, people. Go grab a copy for free. Chemical diversity on small scales. Abundance analysis of the Tucana V ultrafaint dwarf galaxy. And Terese, take us away.
Well, yeah. So first of all, thank you to my co-authors for joining in on this project, especially Josh Simon, who's actually the guy who collected all this data and who is the reason why I'm doing ultrafaint dwarf galaxy abundances in the first place. So Josh was my supervisor at Carnegie Observatories, where we started looking into this project.
Cool.
So in this paper, we have looked at this system, the Tucana V dwarf galaxy, and we find a remarkable chemical diversity, as the title says. So in the recent years, there's been an explosion of satellite systems found around the Milky Way in a variety of photometric and spectroscopic surveys, and in particular, the Dark Energy Survey has found a large amount of these small systems. The question that has sort of appeared is, what are they? Are they dwarf galaxies? Are they global clusters? What exactly is it that we're looking at? And a lot of the times, this is not really possible to say just from the photometry. So we need spectroscopic follow-up.
Yep.
And for this particular system, Tucana V, Josh did some spectroscopic follow-up, but he wasn't really able to figure out whether it was a dwarf or global from that either, because it didn't actually resolve or he wasn't able to resolve a metallicity dispersion or a velocity dispersion, which is sort of the two key signatures that this is a dwarf galaxy.
Right.
So in order to investigate these things further, what we really need is high-resolution spectroscopy and the chemistry of the systems, because that's where we can say something about the chemical evolution and whether they were able to retain the ejecta from supernovae, or what type of system this might have been. So that is what we did with this paper.
Okay.
And I can see you've zoomed in on there that this is just the specs about Tucana V, that it's quite low luminosity, quite small system, located about 55 kiloparsec away. So it's really a good candidate to be an ultrafaint dwarf galaxy, but we didn't quite know.
What are you?
Um,
Okay.
so if we go down to figure 1 to start off with, this is sort of the discovery
Ooh, nice.
figure. So as I said earlier, Josh had followed up this system in a previous paper that he published in 2020, I think, and where he found the 3 dimmest stars. So the 2 Brosa points, yeah, those 2, and then the red point in the middle, that one. And so of those 3, only the sort of that one was available for high resolution spectroscopy. Those other 2 were sort of too faint.
Okay. Right.
And obviously, 1 star is not really enough to do a chemical inventory of the galaxy. So what he did was that he went through the Gaia data and found 2 more candidates that were kinematically comparable to the galaxy, which are the 2 brighter stars in these diagrams.
Cool.
Those 2, yes.
Yes.
But as you can see on the diagram on the right, those 2 are actually located quite far out in the galaxy. So the contours that are drawn on this plot is the half-light radii, or the numbers of half-light radii.
Okay.
And these 2 stars actually lie out at about 7 to 10 half-light radii from the center of the galaxy. So something weird must have happened in this galaxy for them to sit all the way out there, for the 2 of the brightest stars in the galaxy to sit all the way out there. And the question is, are they even members, right?
Well, you could ask that, yes.
Yes, that's a very legal question to ask.
Fair question.
So we got high resolution spectra of these 2 stars as well. So now we have a sample of 3 stars that we have high resolution spectra of. We took spectra with the Mike spectrograph at the Magellan telescope down in Chile, or Josh did.
Nice.
And if we zoom down to table 1, I think.
Let me ask one question. What is the blue?
Yeah.
What is the blue diagram?
Oh, that's the movement of the galaxy in the plane. So that's sort of the trajectory of the galaxy. Yeah.
Got it. Okay.
It's one of the theories is that it might be in the process of being tidally stripped by the Milky Way. That might be why it's puffed up like this.
Right.
Yes.
Good. Okay. Down to table 1.
Yes, which is I think the big observing table.
Mm-hmm.
Where we see that the stars actually have, so the 2 outskirt stars are Tucana 1 and Tucana 2, if I remember correctly.
Oh, okay.
And
So
the center one is Tucana 3 or Tucana 5-3.
Okay.
So that's the one that was found first, and then the other 2 were the ones that were found with Gaia photon or Gaia kinematics.
Right.
And the velocities of these stars match what we expect, but Tucana 1 or Tucana 5-1 actually turns out to be a binary. So there we had to follow it up a lot of times to get a systemic velocity and figure out that the systemic velocity matched the system.
Got it.
But we believe they're all members of the galaxy Tucana 5. So we proceeded with the abundance analysis of these 3 stars.
Okay.
And we did a standard spectroscopic analysis. I can go into details with the parameter derivation and stuff like that if interested, but
whatever you like to cover.
Sorry?
Whatever you like to cover, it's perfectly fine.
Yeah, well, it's pretty standard procedure. We determined the temperatures from photometry, and we did the gravities from ionization balance and velocity, obviously, from equivalent width of the ion 1 lines. And that leads us to the stellar parameters that are, I think, are listed in table 2.
Let's go
probably.
2. So,
and the first evidence that this is actually a dwarf galaxy, because as you can see in the right-hand column of table 2, we have quite a large metallicity spread between these 3 stars. So they cover more than 1 dex in metallicity, which suggests to us that it's definitely a dwarf galaxy and not a cluster.
Okay, cool.
Cool.
All right.
And otherwise, I mean, there's giant stars. They're not anything particularly interesting about the stellar parameters. So the actual abundance analysis is what is the more interesting thing. And since these are pretty mel poor, we couldn't get that many elements, but we did get quite a few. So let's see, where we're going to go. We probably want to go all the way down to the big, massive figure on which is figure 2.
There's the abundance analysis, which we'll look at in a minute. Let's go down to figure 2. Here we go. Here it is visually. Very good.
Yes.
Just to remind myself, these are giants, right?
These are giant stars, yes.
Okay. Okay.
So yeah, this is a sort of this is the massive result of the paper.
Right.
This is all of, so what you see here are the abundances for all the different elements that we looked at. And the Tucana V stars are the black stars, and the other colored dots are other ultrafaint dwarf galaxy stars, and the gray dots are Milky Way halo stars.
Okay, gotcha.
And there's a couple of interesting things to zoom in on here. First of all, the very top plot, the carbon plot, shows us that the most mel-poor star in this galaxy is actually carbon enhanced. So that is a CMP star.
CMP star. Okay.
Yeah, I love those. Those are some of my favorite stars. It actually also has some enhancement in light elements like sodium, which is right next to it. Silicon just below sodium. That star is also quite enhanced in silicon, and also quite enhanced in magnesium as we come more to the right. So this is a fairly special CMP no star, but we'll talk more about that later.
Yeah, interesting. Okay.
The other thing that is interesting, well, overall, when we look at this, we sort of see that the abundances of these stars are quite similar to other ultrafaint dwarf galaxy stars. We have some very low manganese, yes, and we don't actually know why that is like that. It should be said that the lines that we used to determine these abundances do have large NLT effects. So this is the resonance lines, but no other lines were present in the stars, which does support the very low abundance. So yeah, and there are other stars down in that range. So, but yeah, when we get down here, we get to the neutron capture elements, which for ultrafaint dwarf galaxies is usually very low, and that's usually a signature that you have found an ultrafaint dwarf galaxy. This is also true for 2 of the stars. So for the most mel-poor star and the sort of middle melicity star. But for the most mel-rich star, we actually see a small enhancement in neutron capture elements.
A little bit.
And in particular, it's a little bit above the others. And in particular, we were able to get a europium abundance in this star.
Nice.
So if you see at the bottom, the other 2 only have upper limits, which is the triangles, whereas this one star has the europium abundance.
Got it. Okay.
So already now we have a carbon enhanced star, and we have a star that is slightly enhanced in neutron capture elements.
Yes.
And then a star that looks roughly similar to other ultrafaint dwarf galaxy star. One final thing that I will mention now that you zoomed out and you can see both the calcium and the magnesium plot is that for the 2 most mel-rich stars in the system, you see they sort of swap places in the calcium, magnesium, and magnesium plots. So one of them is high in calcium, low in magnesium, and the other one is sort of opposite. Which means that you have a very large range in your calcium to magnesium ratios in this galaxy as well.
Yes.
Which is also something that we will dive into a little bit later.
Yeah. Interesting.
So yeah, this is a lot of interesting things popped up when we did the abundance analysis of these stars. And we can just show a few of the synthesis figures just to convince people that we actually did find these stars. If I remember where they are, they're probably figure 3, I would guess.
Let's go to figure 3. I do want to come back to that table too, though. Figure 3. So here we got. So
this is the CH band in the 3 stars that we've synthesized. So the black line is the stellar spectrum, and the bluish line around is the best fit synthesis, and the dotted line is a synthesis without any carbon. So you can sort of see the different levels, and especially that the Tucana V 1 star is quite carbon enhanced.
3, and this one's 4. Okay, these are my outliers way out there. Okay, okay, I'm with you.
So you said you wanted to come back to table 2?
Yeah, I wanted to look at table 2. I love the figure, but sometimes I like looking at actual numbers.
I'm very used to skipping the abundance tables, because when you present these, then people looking at tables like this, it's usually a bit confusing to people if they're not used to looking at abundances. But these are all the abundances that we have for the 3 stars.
Right.
And we just list them in different formats, the bracket notation and the log epsilon. And for the Tucana V 2-star, which is the one with slight europium enhancement, we were also able to get abundances of all those other neutron capture elements that you pointed to there.
Down here,
so that's why we have that extra length.
Neodymium.
Yeah.
A couple of
Lots
TIs.
We also did the correction for stellar evolution, the carbon correction, so we have both the original carbon abundance and the corrected one according to the evolution of the star.
Yes.
Which is a good test when you
want
to check for.
They are giants.
Yes, exactly. So they have depleted their carbon a little bit. Yes. One thing to notice in this table is that we actually find pretty good agreement between elements where we have both ionization stages. So for instance, titanium 1 and titanium 2,
yes,
we have fairly good agreement between them, and also chromium 1 and chromium 2 for the 1 star where we have both there. So that suggests to us that the analysis that we've done, or the parameters that we found, are not bad. Let's put it like that. That's a good sign that we've done things correct.
There's a little more robust.
Yeah, exactly.
Yeah.
So yeah, we kind of like that.
Okay. Okay, good. Sometimes I actually like looking at the numbers. I understand the picture; it gets to the point, but there's it's more information in the table. So
that's true. That's true. If you know what you're looking at, that's. But when you present these things, it's people don't really like the tables. So
understood.
That's why I jumped to the.
This is the APJ. We're okay showing.
Yeah, that's true. That's true. That's true.
It's
slightly different.
Different audience. Different audience.
That's true.
Okay.
Okay, so let's talk a little bit more about these chemically weird stars that we have in this in this galaxy. So actually, since you're getting down to, that's what, figure 3. You can, is that figure 3?
You want to go back? Okay, figure 3. Figure 3 is a spectrum.
No, sorry, figure 4 then. Yeah. That's just few synthesis more of different elements, where you can see the variety in the between the stars. I mean, they have quite similar parameters, so the strengths of the lines should be quite similar if they had similar abundances, right?
Yeah.
But especially if you go down to the magnesium, you can really see that there's a large variety between the stars.
Yes, a little bit more variation here.
And also for the barium at the very bottom, you can see the Tucana 2-star, Tucana V 2 star, which really has the strong barium line in the middle, and the other 2 are kind of weak-ish. They're still there, so we're still confident in the abundances, but yeah.
I'm going to zoom out just to get a global of those 3 at once. So they are 3 separate figures. Okay, sodium, magnesium.
And the barium.
Okay, with you. Okay.
So let's talk a little bit about that CMP no star that we found.
Yes, because those are always fun.
Yes, they're not unusual in ultrafaint dwarfs. We've found them in multiple other ultrafaint dwarfs before. So it's not really unusual to find them there. But there's a big question of whether they come from, because we don't really know what causes the abundances in these, or the carbon enhancement in these stars. I myself have done decades of radial velocity monitoring of these stars, which has shown that they're mostly single stars. So it's not a transfer from a binary that causes the carbon in these stars.
Yeah.
So it has to be something in the cloud that they were born out of.
Okay.
And there are different theories. There are these spin stars that are these massive rotating metal-free stars that has a lot of mixing, and that can then produce a lot of carbon that puff up in winds, and then you get a CMP star from the ISM. There's also these mixing and foldback supernovae that basically only expels the outer layers, which are where there's a lot of carbon, and then the inner layers, which are more iron-rich, they don't get out, so you get this carbon-rich ejecta.
Yes.
But yeah, we don't really know. And then there are some of them, like the one in this galaxy, which also has enhancements in like light elements, so like sodium, magnesium, silicon, aluminum.
Yep.
And we simply have no idea where they come from. They exist. That type of CMP stars exist in the ultrafaint dwarfs as well. They also exist in the classical dwarfs, but we don't really know. It should be said that this particular CMP star, it has a very low barium abundance, which means that it's a CMP no star. So it's just carbon enhanced.
Right.
But what I did when I found this star, and I sort of did a collection of CMP no stars in ultrafaint dwarfs. And this is figure 7 that we can have a look at.
Yeah, let's go down to figure 7. There's our 3 long, 6 and 7 is a vertical here. So let's see that. Okay, left side here.
So what I did in these two panels is to compare the abundances of CMP no stars in ultrafaint dwarf galaxies with theoretical predictions of where they should come from.
Okay.
So the top one is taking the model from Rossi et al. 2023, I think, where they basically model the Buddhist 1 galaxy and try to reproduce these population of carbon stars in that galaxy. It's also an ultrafaint dwarf galaxy. And they put in yields from population 2 and 3 supernovae and AGB stars. And they find that if the absolute carbon abundances of the stars are high, then they are likely to originate from population 2 supernovae. And so this is this dashed line at absolute carbon of 6.
Got it.
This one.
Okay.
And if the stars lie below this, then they're more likely to be the descendants of population 3 supernovae. So we can see the Tucana V star is quite up in the, so this is the black star, is well above in the sort of
demarcation.
Enriched by, multiple supernovae has gone off. This is a population 2 enrichment. Another theory came from Hartwig in 2018, where they used the magnesium over carbon abundances to split stars up into what they call mono and multi-enriched. So basically stars that had one progenitor, so were enriched by only one progenitor, and stars that had multiple enrichment events had happened to the system before the star formed. So those are these two areas again. So the purple area up at the top there has multiple enrichment events seen, and the blue area at the bottom is already mono-enriched. And again, the Tucana V star is sort of up in the multi-enriched scenario. But the funny thing is these two theories, or these two theoretical ways of looking at carbon-enhanced stars, have roughly the same fraction of sort of population 3 supernovae, population 2 supernovae enrichment, but the stars change places, not exactly to the Tucana V stars, but if you look at some of the other dots in the diagram, then they don't agree on which stars are multi and mono enriched. So it's clear that we need more stars. That's the answer. That's my answer to everything. We need more stars.
Because three could use a few more partners. Yes.
Yes. And we need, what we really need is one system with more stars, where we got the abundances of more stars. That would really help. One slight curiosity about this CMP no star in Tucana V is that that's actually the one that we found to be a binary. So in principle, it could have had a mass transfer from a binary companion. We don't really find that to be likely, though, but it is an option. And yeah, you can see figure 8 there shows the orbital plot for this star.
Okay. A little wiggle.
There is
No.
some fraction of CMP stars that are binaries. And it has actually been found, at least in the Milky Way halo, that the binary CMP stars have higher absolute carbon abundances than the non-binary CMP stars.
Okay.
But if we look at that for the ultrafaint dwarf galaxies, then if we look at the top panel of figure 7, you can see that, well, Tucana V is sort of in the middle range of the absolute carbon abundances.
Okay.
And there's one other, which is in reticulum 2, which is also a binary, and that's sort of sits in the roughly the same area. So whether this trend from the halo can be transferred to the dwarf galaxies is kind of out in the open still. It's we don't really have enough data to say if that's a thing.
Yep. TBD.
Yeah, exactly. So yeah, so that was the CMP no star.
Okay.
Then if we go in the other direction, which is the R1 star, the neutron capture enhanced star, which we did get some extra abundances for, we can actually just make a jump down to the appendix where we show the synthesis of these extra neutron capture lines, which is figure B1, just to jump around a little bit.
All good. B1, there's our neutron capture lines. Oh,
yeah.
Yes.
Just to see, I mean, they are pretty weak lines, but they are definitely there. And so we have all these lovely neutron capture elements.
Very good.
Yttrium, lanthanum, dysprosium, neodymium. Yeah.
Very cool.
All of them there.
You got them. Okay.
Yeah. And that allowed us to make figure 9, which we just came from.
Yes, let's go back to figure 9, which is our absolute abundances of neutron captures.
Yes, which is sort of the standard thing we do. So first of all, we found out that the barium to europium ratio of this star was less than 0, which suggests that it's a rapid neutron capture process that enriched this star. And then we make this plot, which is the standard thing. We take the absolute abundances of the star and we compare them to the scaled solar R and S process patterns. So the solid line is the solar R process pattern and the dashed line is the solar S process pattern. And we see that at least for barium and sort of upwards, we have a decent match to the solar R process pattern. So that confirms that this was probably an R process. For the light elements, the match is less good, but we also see that in Milky Way halo R process enhanced stars. So there's something to go into there, which we're doing with the R process alliance, and that's a whole other paper, which will probably come out soon. But in this case, we're pretty confident that this is an R process enhanced star.
Nice.
Again, this is not the first time we've seen these in ultrafaint dwarf galaxies. There's been others. People probably remember the very famous Reticulum 2 galaxy, which had a large fraction of stars being highly R process enhanced.
Yes.
But there are actually 2 others as well. There's the Tucana V galaxy, which had all of the stars were R1 stars, like this one, so mildly enhanced in R process elements. And then there's the Gru 2 galaxy, which I published in 2020, I think, that also had 1 star, which was an R1 star. And as people probably know, there is, again, a large discussion on where do these elements come from.
Yes.
We had the neutron star merger, which is all good, but there are some problems, especially with the ratios of the light to heavy elements that was found in the neutron star merger or in the 2017 event. We did a paper some years ago where we looked at the lanthanide fraction, which is roughly speaking the ratio of the light to the heavy, and compared the fraction in the R process enhanced Melpor stars in the halo to that of the 2017 event. And we found that, exactly. And we found that the 2017 event was basically too lanthanide poor. It did not produce enough lanthanide material to match the highly R process enhanced stars in the Milky Way. So either that event wasn't representative, or we need some other source to produce the R process that we see in these. And just a quick check for whether what could be, or well, a quick check of if there's any similarities to the R process that has happened in other ultrafaint dwarf galaxies. I did this, calculated the strontium to europium ratio, and found that in Tucana V, we found a strontium europium ratio of minus 1.6, which is roughly the same as we see for the R1 star in Group 2. It's roughly the same as we see for the R2 stars in Reticulum 2. But it's somewhat higher than what we see for the R1 stars in Tucana 3, where we only had a ratio of minus 0.6. But this suggests that whatever event enriched the 3 first galaxies could probably be a similar kind of event. Whereas Tucana 3, well, something else might have happened there. There are other issues with Tucana 3 which might explain why it's not in this bunch. But at least, I mean, the more we find of these stars in these small systems will tell us more about the R process and where it goes.
Nice.
I think it's really interesting that we are finding more and more systems with just one of these types of stars instead of the whole enrichment, which is because that tells us something new.
Yes.
So let's go to the final chemical peculiarity about this galaxy, which was the magnesium to calcium ratio that I alluded to in the beginning. So here, we kind of want to exclude this CMP no star that we found, because the high magnesium that we find in that star might be connected to the carbon enhancement. So it's a bit difficult to, so we'll keep that one out of this discussion. But the other 2 stars, which is one star in the outskirts of the galaxy and one star in the center of the galaxy. If we look at theirs magnesium to calcium ratios, they span almost 1 dex. And if I remember correctly, yes, almost 1 dex, which is a huge range if they were born out of the sort of the same in-cell medium, well-mixed, small galaxy, low number of supernova events. It shows that this galaxy has had to have a extreme chemical inhomogeneity in the gas. I mean, there has to be events happening uncorrelated and not mixing, basically.
Right, not mixing.
Yeah, exactly. And this is not really seen that many times before. It's seen in one other ultrafaint dwarf galaxy that we have this huge spread in the calcium to magnesium abundances, and that's the galaxy that's called Tucana 2. And here it's also the stars in the outskirts of the galaxy that drives this chemical diversity.
Interesting. Okay.
So yeah, that is interesting. Some of the ways that you can get this this large variety in the calcium to magnesium abundances is range in type 2 supernova masses. But you could also have some injection from a type 1a supernova. A sub-Chandrasekhar mass type 1a supernova can give this injection of calcium to the galaxy without actually changing the iron peak elements, because we have to remember that we can't just put type 1a supernova in to lower either the calcium or magnesium, because the iron peak elements are sort of the same as.
Yes.
So yeah, but one of the ideas they had for Tucana 2 was that it might have experienced a merger very early on. And that, of course, could also be the case for Tucana 5, which could also explain why we find some of the brightest stars in the outskirts of the galaxy. But yeah, really, it is just a remarkable chemical diversity in such a small system.
Very cool.
Yes.
Very cool.
So yeah, these are sort of the 3 chemical peculiar stars that we found in Tucana 5, and which we, from the abundances of these, we very confidently say that this is definitely a dwarf galaxy. But it also tells us that maybe to learn the chemical history of these systems and really dig into different nuclear synthesis channels that we hope to explore with these low mass chemically simple systems, we should maybe look a little bit more in the outskirts of the galaxies and not just in the centers, because that may be where we learn how these systems really look chemically. That, of course, takes some work, but hopefully we'll get there at some point.
We'll come back to that.
So,
very cool. Very cool. Beautiful. Beautiful work. Terese, thank you so much for walking us through your very awesome APJ article. Let's see. And you mentioned it a couple of times. So let me just push on it a little bit. And where do you think we go from here, given the published article? Are there any plans to try and get more than 3 stars from this particular galaxy, like maybe 10 times as many? 30?
Well,
are there other wavelengths? Are there, just sort of next steps on where do we go? Maybe not with specifically the Tucana V, but in larger sense, or however you want to.
Yeah, so the problem with these systems is that they're so really faint. So with current instruments and telescopes, it's really time consuming to get more stars. So currently we don't have plans to follow up any more stars.
Okay.
Talk to me again when we get the 30-meter telescopes, and I can actually observe some of these more faint stars, because then I would love to do a more complete analysis of these systems and get more than just 3 stars.
Yes.
There is work going on to find stars in outskirts of these galaxies. So hopefully that will lead us somewhere. But I think in terms of where I want to go with this and where I see the most potential, it is to find the streams that have, so these systems that have gone too close to the Milky Way, the Milky Way sort of said, oop, nice little snack. And then we find those streams. And that's where we can hopefully probe larger samples and probe more of the chemistry of these systems. They're just really hard to find because they're really small, right?
Yeah.
So we do have a few that's streams that seem to originate from ultrafaint dwarf galaxies that we're working on at the moment. And so hopefully that will be where we get the next sort of big move from in this sense.
Very cool. Very nice. Well, I really look forward to seeing that develop over the next couple of years. That'll be very exciting to see. Very cool. Terese, thank you so much for walking us through your very lovely APJ article. Thanks.
Yes, you're welcome. Thank you.
And that will do, everyone. And I hope this made your astronomy day just a little bit better. And we will see you on the next one. Bye-bye.